This is a short podcast regarding quiz number one, scientific method of investigation. So what I'm going to do is just go over the answer and the correct answers to the five questions on this quiz. And if you have any more questions, you can feel free to see me before school or after school. So we're looking at number one. A student doing a mold experiment puts two slices of bread in separate see-through plastic bags. She leaves one bag on the kitchen counter and puts one inside a closed empty shoebox. Her house thermostat is set at a constant 19 degrees Celsius. She monitors both slices of bread daily. What is the independent variable in the student's experiment? Now, without getting into an argument whether this is even a valid experiment, you're looking for the independent variable, which is what she is changing. That's what the IB does. So she has bread in the closet and bread outside the closet. This is the closet. So, and if this is the bread, and that's the bread. So what is different between the two? That is the one thing you have to ask yourself. The thermostat is set at 19 degrees Celsius. That relatively isn't going to change. Two slices of bread in each pile. They're both in see-through bags. One's on the counter here. One's inside the closet here. Looking at all the answer choices, what is she actually changing? And the correct answer here is going to be A, an absence of light. There's no light inside the closet. There's light on the counter. That is the one thing that she can directly change. The presence of mold she can't control. The temperature in the house she certainly controlled. The total number of bread slices she controlled. But the one thing that she can actually change is the absence of light. I'll erase this. Number two is tricky in its wording. But again, it is a independent variable question. A constant amount of heat is added to a quantity of water while its temperature is measured every 3 minutes. What is the independent variable? So let's say we have a glass of water here, so we have another glass of water here. It doesn't really say that the quantity is even, but we'll go ahead and assume that the quantity is even each. And then you're adding a constant amount of heat. What does that mean? A constant amount of heat just means that whatever heat you're adding is going to remain the same throughout. So if I add 100 degrees of heat here and 105 degrees heat here, that it'll always remain 100-degree temperature throughout the course of the experiment, or it'll always remain 105 degrees throughout the course of the experiment. So looking at this setup, what is the independent variable? Remember, I change. So here we have H2O, H2O, and just looking at my drawing, what is different about the two? And it is the amount of heat that is added to the water. So it's going to be choice B. If this still doesn't make sense, come please talk to me about it. But again, what you're looking at, what you're looking for is what is the experimenter changing? What is going to be different about each setup? Going to number three. This was a really hard one. You got this big complicated thing to digest, which is the dependent variable. What are you actually measuring here? And there's lots of measurements if you look at the table, but there's only one thing that you can actually see, that the numbers are going to be a little different based on whatever it is you're changing. So you have experiment 1A and 1B, both are going to use aluminum with the same specific heat, of course. Specific heat is a number for every substance on the planet. It's the amount of heat necessary to raise a 1 gram substance 1 degree Celsius. So basically, the amount of heat needed to raise the temperature of this particular substance. So right now, because it's the same substance, the temperature is the same. They have two different masses, and then in the end, you're putting this, and it says mass of water in each experiment. It's going to be 125 grams of water. So you're going to set this metal, or dropped, it says right here, you're going to drop that metal into a beaker of water and see how long it's going to take, or what the temperature will be of the water based on however long you're going to let it sit there. So experiment 2A and 2B, you're using copper this time, with, of course, copper has a different specific heat. The temperature of the metal is going to be the same. The mass of the metal is going to be different. And then at the end, the final temperature of the water. So what is it that this experimenter is actually measuring? And I know, again, this was a little tough to digest because we have 4 columns here, 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 and here with 4 different measurements. But walk yourself through this data table and determine what it is the experimenter is actually measuring. What do they want to know? We've given you the specific heat. That doesn't change. We've given you the temperature of the metal. That isn't going to change. We've given you the mass. That's not going to change. So you're left with the final temperature of the water. So if you go down here, that is going to be, oops, sorry, not temperature of the metal, temperature of the metal. We erase that. That should be choice D, final temperature of the water. So again, if this doesn't make sense, then come see me and I will help try and make sense of this question. Going on to number 4. Erase here, number 4. A chemist observes that a large molecule reacts as if it were much smaller. The chemist proposes that the molecule is folded in a way that causes it to react differently than expected, and develops a series of experiments to that proposition. How will the chemist's proposition be classified? Whenever you propose something, it doesn't mean that you have to be right. It's just a proposition. It's just a statement saying what you intend to do or what you think is going to happen. So based on what we know about this terminology, proposal is just a hypothesis. If I change this, then this will happen. Or I believe that this will happen in the experiment. So that is what would be consistent with a hypothesis. Question 5. Question 5 is very tricky, but something you have to get used to when it comes to a lot of questions are that sometimes the words can confuse you. And what you really need to do sometimes with charts and graphs, and a really good test-taking strategy is, number 1, just ignore the answer choices at the beginning. And sometimes even the question itself can have a lot of information that isn't needed. So what I want you to do, those of you who got this wrong, just take a look at this question and say to yourself, what is this graph telling you? Insulin sensitivity, that is what you're measuring, based on the time, and the title is The Effects of Exercise on Insulin Sensitivity in Elderly Women. So looking at this chart, just taking a look, what could you surmise? Well, pre-exercise is right here. That's the dotted line. Post-exercise is the solid line. So where is there more insulin? Pre-exercise. So there's more insulin available, or there's more of a sensitivity to the insulin pre-exercise than the post. So looking at all these answer choices, erase the answer choices now, what would be consistent with that? Just looking at the chart and reading the explanation. That letter B, when you exercise, right here, when you exercise, sensitivity, right there, I'm going to erase that. Just use red. There's your solid line. When you exercise, the sensitivity that is measured decreases in elderly women. So oftentimes you read this and you kind of overthink the question, but what this question is really asking, can you look at a chart or a data table and then interpret the results? So if this doesn't make sense, you, Mr. Matthews. This concludes the podcast on quiz number one.